Yeah. Thanks for the invitation. Sorry I'm not there in person, but it's still nice to actually come and talk to you guys. It's been a while. Yeah, so I'm talking about some joint work that I've done with Alex Blumenthal, who is now at Georgia Tech. He was previously at University of Maryland, and with Sam Puncheon-Smith, who is at the IAS now and will be joining Tulane next year. So he was also formerly at University of Maryland. So the equations that we're going to be studying today are the Navier-Stokes equations, the incompressible Navier-Stokes equations. So those of you unfamiliar with the equations, it's basically Newton's laws. Force equals mass times acceleration. This is the acceleration. So this piece tells you that the velocity actually transports itself, or momentum transports itself. So as the fluid moves, the fluid particles are moving along and transporting momentum. So that's where that fundamental nonlinearity comes from. The two forces involved in the fluid are the pressure. So this is the force that enforces the divergence-free constraint. So it's actually a Lagrange multiplier. So it tells you, if you try to press on the fluid to change the volume, then the pressure is what resists you. Then the other force is the viscosity, and it basically tells you that two layers of fluid slipping past one another feel some friction. So it tends to smooth out the velocity and the diffuse momentum throughout the domain. Now you can check that so F here is divergence free. Just that's the external forcing, if there is any. That you can check by taking the divergence of the equation that the pressure actually solves this just simple Poisson equation. So in fact, this term is actually just kind of a non-local nonlinearity of the same order as this one, but different and more complicated. The parameter nu is the one parameter in the system, so it's the inverse Reynolds number or the viscosity, depending on how you normalize the system. One of the first things you learn about the equation is that if you take the curl of the velocity field, of course, since you know the divergence is free, if you're on RD, everything I'm talking about is RD of the torus or something like that. So that's like periodic boundary conditions in a box. Then you can reconstruct the velocity field using the Biot-Savart law. And the vorticity equations themselves are a beautiful set of equations. This nonlinearity, it's a Lie bracket, and it has a really deep geometric structure that basically tells you that this is the natural conservative way of transporting vorticity. So this quantity is called the vorticity. So in 2 dimensions, the vorticity is like a scalar. So this actually reduces to a scalar transport equation. And in 3 dimensions, it transports vectors in a conservative way. So that a surface moving with the fluid, the flux through the surface of the vector field is always conserved. So it's a natural transport in both 2D and 3D. I basically do all my study at the sort of the high Reynolds number limit. So that's when the nu is going to 0, or maybe when nu is equal to 0. And the fluids can show a variety of dynamics. The sort of 2 extremes are kind of turbulence or some kind of coherent structure where certain special flows are distinguished and sort of show up more often. I'm going to be talking about the turbulence angle, which is sort of when the flow is characterized as being strongly chaotic, when the energy spreads out through a large range of scales. And you also see some kind of small scale universality, which the details of the small scales in a statistical sense don't depend on the experiment. So you see a lot of special things that are not just chaos. So turbulence is not just chaos. It involves chaos, but it's not just chaos. So this is what turbulence looks like in 3-dimensional fluid mechanics. So on this side is just a stock image of smoke coming out of a smokestack, and you see that the flow becomes turbulent, and it generates a whole range of scales. So it's not that it just picks out 1 scale or 2 scales or 3 scales or whatever. It generates all the scales kind of between basically something on this scale and basically a millimeter scale. It fills everything in between. So on this side of the slide, this is a power spectrum. So on this axis, it's log of the frequency. And this axis, it's log of the energy in that frequency, in some average sense. So I'll explain exactly what mathematical rigorous average sense I mean, but it's just like an expectation. So, and the 2 curves are 2 different experiments. This is a physical experiment. They have a wing, and they're flowing fluid over the wing. and it breaks down and goes turbulent in the wing. Looks like this. And the two curves are two different ways of flowing fluid over the wing. And you see at large scales, at the scale of the wing, the curves look totally different, right? They do sort of kind of a normal thing here, and they do some weird, really specific forcing in this other curve. So at large scales, the thing will look totally different. But the point is that if you go to smaller scales, the statistics look basically exactly the same. The only real difference is the net energy that you put in. But the slope of this curve seems to be universal, and essentially all the statistics seem to be universal at small scales. So just like in the smokestack, basically these kind of statistics will be matched also in the smokestack, and basically every other fluid that you interact with. Three-dimensional incompressible fluid that you interact with will have very similar statistics. So this is what I mean by small-scale universality. 2 dimensions, you have turbulence. It looks different. It's in some ways more complicated. I'm not going to talk more about the particulars. I just wanted to give you an indication of what turbulence looks like. So we have a general program about turbulence. So wanting to study the Navier-Stokes equation with stochastic forcing and try to make, there's a lot of theories in the physics literature. Maybe the most famous ones are the Kolmogorov 1941 papers. So Kolmogorov wrote some physics papers in the 40s that sort of revolutionized classical physics. And we made certain statistical predictions about what experiments should observe in turbulence and the Navier-Stokes equations. But we don't have a mathematically rigorous proof of basically anything that we said. And so the program is to try and develop tools towards doing that with stochastic forcing. We're still a long way away from this. And I'm going to talk about just one aspect of this. So our most recent progress, which is about proving the velocity field itself is chaotic. So you may have heard of our other work where we prove that the motion of particles in the velocity field is chaotic. That's different. That's called Lagrangian chaos. It's different. Still interesting, different. So I'm talking about Eulerian chaos today, asking whether or not the velocity field is chaotic. First question you might want to ask is why use random forcing? And there are many reasons for this. The one reason actually is that even if you read a classical physics paper like Kolmogorov's 1941 papers, the simplest setting really in which to study turbulence is to set up an external forcing, send time to infinity, and let it settle into some kind of statistical steady state. And then you send the parameter nu to 0. You want a statistical steady state. So already the word statistical is being highlighted. So using the language of probability and random forcing already kind of makes sense. And more specifically, if you're talking about a randomly forced system or a stochastically forced system, you can construct these statistical steady states mathematically rigorously. And in some cases, you can prove that they're unique and have a bunch of really good properties. And that's actually the main thing about stochastic Navier-Stokes that we actually know how to do, especially this in 2 dimensions. And so this tells us that we actually have objects to study. We have these statistical steady states. With deterministic forcing, we don't have these statistical steady states. And we have essentially no idea how to prove they exist, more or less. And so at least in the random case, we know what we're supposed to study. We just don't know how to prove anything about them, aside from their existence and uniqueness and stuff like that. And also engineers and physicists actually doing computer simulations or physical experiments, they don't see any difference in deterministic or stochastic forcing in general. Okay, so there are a variety of caveats to this. And also from a mathematical perspective, random dynamical systems has much more robust tools than deterministic dynamical systems. And so that's another reason. So as you'll see, random dynamical system plays a central role in the whole program, and especially in what I'm going to talk about today. Okay, so what I'm going to refer to as chaotic in this talk is saying that the top Lyapunov exponent is strictly positive. So given a general abstract evolution on some configuration space, you want to ask, if you take the derivative with respect to the initial condition, does this matrix grow exponentially? So it basically tells you that if you make a small infinitesimal perturbation of the initial condition, the 2 trajectories separate as fast as possible, assuming you have a well-posed system and whatnot. So this is what I'm going to call chaotic. Some people will call it like this, the butterfly effect. There's many different notions of chaos. This is the one I'm using for my talk. So I want to prove that the Lyapunov exponent is positive. Now the difficulty is For deterministic systems, it's really hard to prove. It's really hard to prove that these things are positive. They're only known in a relatively few specific examples that aren't really representative of natural systems. And there's some ridiculously hard open problems about proving positivity of Lyapunov exponents on positive measure sets, even for really simple systems. So doing it for the Navier-Stokes equations just seems really hard. We don't do it for the Navier-Stokes equations yet, but we do it for Galerkin truncation. So we do it for finite dimensional truncations of the Navier-Stokes equations with stochastic forcing. So let me jump to the result, which is proved over the course of 2 papers. So first I have to write down the Navier-Stokes equations, the Galerkin truncation of Navier-Stokes. So don't get too annoyed. Okay, so let me explain what this is. So the unknown W takes values. So what I'm going to do is I'm going to take the Fourier transform of the PDE. So if you remember, the PDE looks like this. So in 2 dimensions, let's use let's use this. So I'm going to take the Fourier transform of this unknown, sorry, of this PDE. So now omega is a scale. I take the Fourier transform, and this gives me a function on the lattice because I'm talking about the solution on the torus. So I have the Fourier modes are indexed over the lattice. Now what I'm going to do is I'm going to cut that lattice off in a square. That's what this notation means. It's a truncated lattice and a square, and I'm only going to keep those Fourier modes. So the square has side length n. I think this is n here. And I'm just going to keep the unknowns here, the Fourier variables here. And then I'm going to write the system in Fourier. And I'm also going to rescale. I'm going to rescale the variables so that the viscosity, so this is the viscosity, and the forcing are balanced. You can always do this without losing generality, and it's convenient. So this is what happens with the nonlinearity. So C is just some particular function. The fact that it's a rational function is crucial to our talk. And then this is the stochastic forcing. Okay, so the theorem says that if you take enough Fourier modes, there's nothing magical about 396. It's probably true all the way down to 2. It's just 396 is what a proof produces. And if your forcing is non-degenerate in a sense called hypoelliptic, so this, I'll explain what this means rigorously, but essentially it suffices to take 4 modes, actually. This was proved by Winona and Jonathan Mattingly in 2001. So it suffices to take a relatively small number of stochastic forcing, just a few modes activated, and this is independent of capital N. It's independent of how big your truncation is. So anyway, under these conditions, there exists a Lyapunov exponent. It's well defined and independent of the initial condition and the random noise path. And for all epsilon sufficiently small, it's strictly positive. And you have this bad quantitative estimate. And of course, this has to come from the nonlinearity, because if epsilon is large, you can prove that the Lyapunov exponent is negative. And also, if the nonlinearity were just not there, you can prove the Lyapunov exponent, so it's negative. This is truly coming from this nonlinearity. So that's the statement that we're going to be proving. Okay, so now let's talk about SDEs as a random dynamical system and sort of build up some of our structure for how to prove this theorem. So I'm just talking about a general SDE on Rn, and I'm going to write it in Stratanovich form because it's convenient for chain rules. So if you don't know much about SDEs and don't know the difference between Ito and Stratanovich, don't worry about it, especially because I took additive forcing here, so that there is no difference for the case that I'm really most interested in right now. So these x's are vector fields on Rn. The important point is this is the deterministic part of the system, and this is the random forcing. So you think of x0 as kind of the most important vector field. And the other ones are kind of whatever, the stochastic forcing. The Navier-Stokes equations are globally well posed in time. The Galerkin-Navier-Stokes equations. The talk, by the way, is on 2D Navier-Stokes, but I'm sure the theorem could be extended to 3D, but you'll see at the end why we have to choose specifically 2 dimensions or something like this for now. So there exists global solutions, and so you have a stochastic flow of diffeomorphisms. So it depends on the random noise path. It's not just, but this basically tells you, given the initial condition, what does the solution look like as a function of future time. Once you have this noise path, you can define Markov semigroups. So this tells you, given the initial condition, what is the probability of finding the solution in a given set? That's the Markov kernel. And this gives you an evolution on observables, which tells you the expected value of some statistical question you can ask. What is the energy? Tells you the expected value of the energy given the initial condition. And this, the dual, is the evolution of the law. So if the initial condition were distributed like mu, then the solution is actually going to be distributed like PT star mu. This is actually the one that I find intuitive. So it's an evolution on the law, but both are useful and important. Especially because we're using finite dimension, we're using a finite dimensional SDE. Both of these Markov semigroups solve PDEs. So these semigroups are subparabolic evolution equations, where these are the PDEs. So I'm using these vector fields as directional derivatives in the direction, so it's differentiation in the direction the vector field is pointing. It's commonly used in geometry, but outside of geometry, everyone finds this confusing. But it's very useful, and I know I found it confusing at first, but now I don't, and realize that it's useful notation. Okay, so the fundamental quantity, one of the fundamental basic things that you want to study in SDEs are stationary measures. So these are measures for which the law is independent of time. The PT star mu is equal to mu. And the important thing to know, if you've never worked with a stochastic system, the solutions, of course, are not stationary. Only the statistics are stationary. The law is stationary. So you should think the flow over a stone in a river. If you stare at this for a few minutes, you'll realize you're looking at essentially a statistical stationary solution of the Navier-Stokes equations. It's very much non-stationary, but the law isn't really changing. So that's what you should kind of picture in your head for what these solutions look like. Under the conditions that I said, I used this term hypoelliptic. Under this condition of the forcing, this solution, there's a unique stationary measure. And the stationary measure, note, solves a PDE. That's crucial for the talk. So it solves this complicated subelliptic PDE. The proving uniqueness of stationary measures is a classical topic. There's many different ways of doing it. In finite dimensions, generally, or even in infinite dimensions, there's two ingredients that are used. There's proving that the Markov semigroup has some kind of regularizations. In finite dimensions, we can use L infinity to continuous regularization, and some kind of irreducibility. It suffices to say that from starting any place, there's a positive probability of going into any open set. That's so it says basically everything is very strongly connected. That is sufficient, but not necessary. But will be true is true for our systems. If you have these two ingredients, then you can prove uniqueness of stationary measures. There's a theorem called the Duke-Kedzminski theorem that tells you this. Notice that you just need regularization. You don't need ellipticity. So you don't need that these vector fields span Rn. They don't need to span Rn. You can still have regularization without that. And that's what the word hypoellipticity means. And there's a more or less sharp condition for figuring out when things are hypoelliptic. And I'm not just bringing it up for fun. It's important to the talk. I haven't explained how yet. Now, once you have these stationary measures, there's a really beautiful theorem called the multiplicative ergodic theorem, which I'm not going to talk about using the full power of this theorem. So I'm just going to use the following two properties, which is that assuming that mu has good tail, it decays fast enough at infinity, you can prove that the multiplicative ergodic theorem tells you that there exists deterministic Lyapunov exponents, in particular the top Lyapunov exponent. So there exists a lambda 1 such that this holds almost surely for every initial condition. And there's a total Lyapunov exponent, which gives you the asymptotic compression or expansion of Lebesgue measure. And they're related like this. N is the dimension, remember. The multiplicative ergodic theorem tells you a bunch of other really interesting things, but that's all I'm going to need for the purpose of this talk. I think the right, or the way I think about the MET is, well, okay, if you have additive forcing, then this derivative matrix will solve an ODE, a kind of random ODE, linearized around WT, which is some time variable trajectory. Now, if WT were stationary, then you would use spectral theory of finite dimensional matrices to determine all the possible exponential growth and decay rates that JT could experience. You could use the Jordan canonical form for that. So what the MET tells you is that if you replace WT with something fixed, if you replace a fixed equilibrium with some ergodic process, then you can still do that, essentially. So it's like an ergodic theory for solutions of this ODE, essentially. So it's a really cool theorem. But the thing is, it's already known. And so the existence of a Lyapunov exponent is not the interesting part of our theorem. That's a consequence of the MET. In fact, you don't even need the full power of the MET for that. What's interesting about the talk is proving that the Lyapunov exponents are positive. This is a hard problem in general because of something that dynamicists is called cone twisting. And I'll explain what this is. So let's consider a simple toy model to see why Lyapunov exponents could be hard to estimate. So instead of thinking about ODEs, let's think about the following problem. I'm going to take determinant one matrices, IID. So I'm going to draw them from a single distribution and multiply them together. If you think about the chain rule and about the solution to this ODE, you say, it's kind of a reasonable toy model for asking about an ODE of this type. Think about the time one evolution of this ODE. And now I want to ask, does this matrix product grow exponentially or not? This random matrix product grow exponentially? So you can come up with some examples when they don't. So the simplest example is, of course, they're all just random rotations. So there's no growth. Another example is this shear, this random shear. So what will happen here is that there'll be growth, but it will be sub-exponential. It'll grow like n or square root of n or something like this. The more interesting example is the following, where now imagine, to see why this example is interesting, imagine p is 0.99999 or something. And so what you'll see is that with extremely high probability, the x direction is going to get expanded and the y direction is going to get compressed. So it's going to be expand, 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 expand. And then eventually the rotation matrix is going to come out and you're going to flip the x and the y axis. And then it's going to be compress, 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 compress. And the thing is that this expansion and compression is going to cancel out. And so you'll get sub-exponential growth. You'll get something like heuristically, so you get something like e to the square root of n kind of growth. But that's still zero Lyapunov exponent. And you can imagine that for any system that's even slightly non-trivial, this is extremely hard to keep track of. You need to know the entire global and time trajectory. It just takes one flip somewhere in that entire lifetime for everything to be ruined. So it's extremely hard. That's why you need randomness, essentially. Because the randomness is going to help you overcome this cone twisting problem. I think the most, a theorem that I found really staggering cool when I first learned it, is I still think so, it's a theorem of Furstenberg, which roughly says that up to a deterministic change of basis, these are the only sort of possible cases where lambda is equal to 0 for this random matrix model. It's an incredibly beautiful theorem. It uses the algebraic structure of matrices and cool multiplicative ergodic theory techniques. It's just a great theorem. And it gives us hope for random dynamics. Okay, so one of the aspects that I think the idea goes back to Furstenberg, maybe Peter actually knows, is even if you look at the proof of the MET, for example, it'll be clear that the directions, I think it's already clear that the directions of expansion is the most crucial thing to keep track of. And so the dynamicists introduced a variable called I'm going to call it the projective process, This is this is incorrect notation. This is WV. So what I'm going to do is I'm going to take V on the sphere, and I'm going to map it onto the matrix and normalize it. So VT is going to be stuck on the sphere. So VT is not a Markov process, but if you look at the coupled WV process, this is a Markov process, and in fact, it solves an SDE. So you can check that it solves an SDE where these twiddle vector fields are lifted to the tangent space of the sphere bundle with this procedure. So it's a bit of a mess, but that's how it works. So this SDE now has its own Markov semigroups, its own generators, and I'm going to be working under a setting where you have a unique stationary measure for this projective process. So we're going to have to prove that for the Navier-Stokes equations, which turns out to be, well, that's what the second paper is. So it's not easy, but not impossible. So the stationary measures of this CT process encode statistics about what directions are stretching and compressing. So that was kind of clear by design. One can formulate formulas that relate the stationary measure. So I'm going to call the stationary measure nu. You can relate the stationary measure nu directly to the Lyapunov exponents with something like this. This you can prove using the ergodic theorem. But I have no idea how to use this formula to get quantitative estimates on anything, because this integrand this could be negative, could be positive. Who knows? It's going to cancel out in really complicated ways. I have no idea. I think a much more interesting and deeper identity, or sometimes an identity, sometimes it's an inequality, depending on the setting, is the following, which is a bit complicated to explain. So I have a stationary measure on the sphere bundle, nu. I can kind of disintegrate it with respect to the measure on the original process, mu. And then for each W, I have a measure on the sphere, which in one dimensions I'll draw as a periodic interval. Does that make sense? I mean, think of it as a density with respect to some underlying Lebesgue measure, and I can just look at the dependence on W, or sorry, I can just look at the dependence on V with W fixed, more or less. So I have a measure on each individual sphere. So then, under certain conditions, I can prove that the let me try to move this picture so it's. So I have point and the measure, point and the measure. Now what I'm going to do is I'm going to flow the process forward under the random flow map. And so I have a measure at the beginning and a measure at the end. And then, or I'm going to push the measure forward under the gradient action. So I can push this forward. Let's do a different color and get a different measure. So this is grad phi star mu. In some average sense, these kind of have to be the same, but not pointwise in omega or pointwise in W. There's no operator to be the same. They sort of have to be the same in an average sense, sort of. But they're not the same in general. And it turns out not only not the same, but the relative entropy between these two measures, if you then average over all trajectories and all initial conditions, gives you is directly related to the Lyapunov exponent gap. And it's a really cool, it's a really cool identity. It's not as hard to prove as it looks, but it's still not that easy to prove. So it's a deep inequality or identity in this case. I think the key consequence to point out is that these two things can be equal if and only if you have this all-assured degeneracy. That's a lot of rigidity. And Furstenberg used this approach to prove this theorem about the three cases. So these techniques are called a la Furstenberg now, from his 68 paper, because this implies a whole ton of rigidity, and it's relatively easy to rule out that this is possible in some cases, or in a lot of cases. And so actually, Sam and Alex and I's paper on Lagrangian chaos for stochastic Navier-Stokes, that actually did the infinite dimensional version. We used a version of Ala Furstenberg to prove that, because the flow generated by Navier-Stokes, like the flow of the actual particles, this is volume preserving, and so lambda sigma is 0 in the Lagrangian chaos problem, which means all you have to prove is that lambda 1 isn't equal to lambda sigma, and then you have chaos. Okay. But the problem is, if lambda sigma is not 0, then I don't know how to use this technique to prove positivity. You could probably prove that n lambda 1 is strictly bigger than lambda sigma, but it doesn't tell you that lambda 1 is positive. And closely related to that, it's not quantitative. This technique's not quantitative. It either works or doesn't. So the first thing that we did was we found, as far as we could tell, a new identity. I'm not saying that no one ever observed it, but we could not find it written down in a paper. So basically what we did is we found an time infinitesimal version of this relative entropy identity. So you can actually kind of formally compute this, and you can even find some conditional version that really matches exactly what the identity is trying to say in a time infinitesimal sense. But it's not actually the version that I'm going to use today. The version I'm going to use today is this one, which, so F is the density of the stationary measure nu. Maybe I'm being a bit pedantic. Just think F is nu. It's the stationary measure for the projective process. Then what you can say is this Fisher information type quantity balances more or less the Lyapunov exponent gap. I know there's a 2 floating around, but it's not important for the talk.
Okay. Jacob, a quick comment. Yes. The first one of those 2 equations, the one you don't use because it's much less useful, I actually proved it it's in a conference paper.
Oh, really?
In the mid-80s.
Could you give me the citation? But you didn't prove the second one?
No.
Oh, okay.
No.
Okay.
Yeah. I had other reasons for proving the first one, which didn't extend to the second at that stage.
I see. Okay. Yeah.
It was before I'd thought about the entropy argument, and I guess I never really returned to that.
I see.
But I'll send that information. Yeah, sure.
Okay. Yeah. Thanks a lot. Yeah. Okay. So this right. So this is a Fisher information like quantity, and the reason it's useful is that now imagine we're trying to do something quantitative. So we're putting a square root of epsilon in front of the forcing, and the vector fields are allowed to be parameterized to epsilon as well, and that's important for the problem we want to solve. Then if you track the epsilons, you have that this Fisher information thing balances this ratio where epsilon appears there. The reason why it's potentially useful is that it's time infinitesimal directly on the stationary measure, unlike the relative entropy formula, which involves this sort of random paths and random push forwards. It's really hard to keep track of that. I don't know how to use this formula in a quantitative way. But like the relative entropy formula, this is a non-negative quantity to estimate. So it's much easier to estimate from below than the formula coming from the ergodic theorem, or something called the Furstenberg-Kazminski formula, if you're familiar. Okay, so now here's where hypotheticity is going to come in a real way. So the point is that this Fisher information here contains only the directions that you're forcing in. And so it doesn't contain the other things. So it doesn't tell you that some Sobolev regularity bounds from below this quantity. But that's what I'm going to prove, or that's what we are going to prove. And so now we really have to get into Hormonal's condition of hyperelliptic regularity theory. So this is how do you prove that your Markov semigroup is regularizing without ellipticity? So Hormonal codified this. So Kolmogorov actually was the one who wrote the first paper on hyperellipticity, to my knowledge. But Hormonal was really the one who codified it and found this sharp condition. So if I have a general set of vector fields, so just think a general SDE on a manifold. This guy is kind of the distinguished sort of drift vector field, the distinguished deterministic part. And these guys are the forcing vector fields. Then I'm going to build this collection, these successive families of vector fields. So script x0 or script x naught is just the forcing fields. And then each next script xk is the previous ones plus all commutators of the previous ones with all these vector fields. So if I eventually get the entire tangent space of the manifold, then I'm going to say that this satisfies the parabolic harmonic condition. And you can see that ellipticity or strict parabolicity or whatever of the generator is the case when script x naught spans the tangent space. So this is a strict generalization of strict ellipticity. So you're no longer saying that script x naught has to be enough to span the tangent space, but if you just do a bunch of commutators, if you eventually get to the end, then you satisfy Fermat's condition. So I'm going to call this PHC, parabolic harmonic condition, and if the lifted vector fields are hyperelliptic, I'm going to call this projective PHC. So we're going to need that the lifted vector fields are hyperelliptic, not just the original vector fields, which was proved by Wen and Jonathan Mattingly in 2001, but the lifted ones. So if that's true, if you have this parabolic projective, if you have this projective PHC in some kind of uniform and epsilon sense, and the vector fields are uniformly controlled, then you can prove the following PDE estimate, which tells you that the solution, so you look at a solution of this PDE with, which is negative and norm 1 in L1. F epsilon's a probability measure. That there exists a number S star, and for every bounded set, there exists a constant C, so that this inequality holds. And the point is that neither C nor S star depend on epsilon. So the generator depends on epsilon, but there's an epsilon in front of the second order terms in the generator. So the generator basically looks like Laplacian in some variables. Basically, if you have kind of not stochastic, if you don't have multiplicative forcing plus a deterministic piece. So the generator depends on epsilon, F depends on epsilon, but the inequality doesn't depend on epsilon. That's the important thing. So C and S star are uniform in epsilon, which means that I can take my identity for the Fisher information and get this lower bound. And the only place where epsilon appears explicitly is here. And possibly here, here, and here. But the point is that it doesn't appear in capital C and not in the star. The S star is actually, you can explicitly relate it to the kinds of brackets you need to do to find spanning. Capital C is some really complicated constant that I can't quantify. So how does this theorem work? Let me just give well, actually, I don't have time to do a summary. Let's just say Hormonal's original 1967 paper was based in an L2 framework, but his arguments are really robust and very clever. And so this inequality that we have is essentially an L1 version of Hormonal's. It's a consequence of an L1 version of Hormonal's theorem, where you're keeping a lot of track of what's happening with epsilon. So you have to get the kind of right optimal inequality, which Hormonal says what it should be in L2. And so you have to do the L1 version. Switching to L1, Hormonal uses the L2 framework. He definitely uses it, but you can do it in L1 as well. So it's not easy to adapt to L1, but it's also, you don't have to use a completely different proof. So Hormonal, this is essentially one real step that's really hard to adapt to L1 framework. So it's a technical big PDE estimate to do, but I don't have time to discuss, so I will continue. Okay, so now let's see how to apply this theorem, this lower bound on the Lyapunov exponent gap. So consider just a general class of SDEs on RD, or like switch from D to N, it's okay. So this is the dissipation, the damping. So A just has to be any symmetric positive definite matrix, and B is the nonlinearity. It just has to be bilinear and satisfy these two conditions. Then I'm going to study this general class of SDEs. The 2D Navier-Stokes equations and also the 3D Navier-Stokes equations, the Galerkin truncation, are special cases of this SDE. For all versions, for all systems in this class, we can prove that projective PHC is sufficient to imply this positivity and probably suboptimal quantitative lower bound. So we use this to prove chaos for Lorentz 96 in the original paper in dimension. Lorentz 96 is a toy model that's used in the applied mathematics literature to test numerical methods and semi-analytical methods for high dimensional chaotic systems. The traditional dimension is 40. We can do it in dimension bigger or equal to 7. But Lorentz 96 is much simpler than Navier-Stokes as a system. So we were able to do it. So we were able to do it in this original paper, but we need a second follow-up paper to prove projective PHC, this projective Hormonal condition, for the actual Navier-Stokes equations. So this is a bad quantitative estimate. There exists good quantitative estimates for much simpler systems. For example, Peter has a work on a 2D nonlinear oscillator. And these papers are hard. So the systems they're studying are simple, but they're getting much more precise understanding of the Lyapunov exponent. The thing is, that requires a pretty much almost exact understanding of the projective stationary measure. And possible for simple systems, even for simple systems, not super easy. But I mean, it's not easy at all, I would say, actually, even for these simple systems. But for these really hard systems, I don't think we'll ever have this understanding. And so the purpose sort of the method was to design a set of techniques for which you could do something like prove chaos without a complete understanding of the system, which I think is only really possible for random systems. But I don't know. Okay, so here's the basic idea of this conditional theorem. The first step is to verify all the qualitative properties I claimed. Just starting from projective PHC, this is a good exercise in stochastic in SDEs and their associated PDEs. Then you use the fact that the nonlinear is divergence free in configuration space. So this is the Liouville property. And so you know what lambda sigma is, epsilon times the trace of A. Since we're in finite dimensions, the trace of the Laplacian is finite. And then you plug that into your Fisher information identity and use the quantitative hypothetic lower bound theorem. And you have this. And now you can guess where we're going, because this is sort of like 1, this is 1. And so the only thing that could blow up is this ratio. So you say, all right, let me assume for contradiction this is bounded. Then I get compactness of the stationary measures in epsilon. Compactness strongly in L1. And it's important to emphasize that it's strong in L1. You can always pass weak star as measures. But here it's important actually that we can pass and get an absolute continuous density for the deterministic limiting system. And here we have to use a little bit more dynamical systems. So we have to use a lemma from deterministic dynamical systems that tells you that there can't be an L1 invariant measure to this deterministic system if there's any unbounded growth. So the thing is that with random systems, so we know that expansion in the gradient will cause compression of the projective process. So this is because the projective process will tend to tip in the direction of expansion. And so if there's expansion, the projective process will compress. So it literally looks like compression on the sphere. And in a random system, this compression can get averaged out, and you'll get smooth stationary measures, even though you have chaos. So this is what happens for Navier-Stokes, for example. So you have smooth stationary measures on for the projective process, even though you have this unbounded growth, because it's always happening in different directions, maybe, and it's getting random and it's getting kind of averaged out. This can't happen in deterministic systems, and so you can prove actually that you get concentration, you get, so infinite time concentration if you have any unbounded growth of the gradient. So because of the fact that the nonlinearity is a second degree polynomial, or it doesn't, the second degreeness isn't important, but the fact that it's a polynomial is, we can actually prove this gradient growth even though we don't know that much about the system. So it kind of comes from the energy scaling, or from the scaling invariance of the nonlinearity, that essentially trajectories on every energy shell look the same, just rescaled in time. And you have a nonlinearity that ensures that they're really kind of moving at different speeds. And so this kind of so this is about how to break the scaling lambda over epsilon. It's not a sharp estimate, because if you think about it, should be able to use similar arguments for completely integrable systems if they're projective hyperelliptic, which for some systems may just depend on putting enough noise in, for example, if you want to use multiplicative noise. So the point is that you don't need to know everything about Navier-Stokes. You don't even need to know that much about the nonlinearity at this step. But I see that was by design. We designed the method specifically to do that, because we don't know that much about Navier-Stokes. Okay, now the last step, you actually do need to use the Navier-Stokes nonlinearity a lot, which is to prove projective hypotheticity. So the point is that it isn't so hard to prove hypotheticity, but once you lift this vector field onto the tangent space of the sphere bundle, it was a lot less obvious. Now, so this was proved in a follow-up work with Sam and I. And now, thankfully, actually, we used a lot of lemmas that Peter proved in an old paper in '89, but using a bunch of special structure about lifted vector fields, and actually we use a little bit of complex geometry formalisms. You can use the fact that the thing is that phase space is flat, so it's just Rn, or it's basically Rn, but you should really think of it as kind of a flat complex manifold if you want to do this step. And then the spanning condition can be reduced to something which doesn't depend on space, right? It doesn't depend on the configuration at all. And also doesn't depend on the forcing, interestingly. So you can reduce it to a question of just, you have a set of matrices, which are basically the second derivative of the nonlinearity. You have just a collection of these matrices. And then you ask, does this collection of real matrices, does the Lie algebra, so if I commute them and take linear combinations, does this Lie algebra span all trace-free matrices? That's sufficient condition. And you see, it depends only on the nonlinearity. It's purely algebraic. And so that's nice. It's nice sufficient condition. But it's still hard because these matrices, I mean, if you just start commuting them by hand, I mean, you don't see anything. I don't see anything. I have no idea how to prove this condition sort of just by playing around. And so we actually had to go and learn stuff about Lie algebras. And one of the things we learned is the following trick, is that if you have a diagonal matrix in your Lie algebra, or just take any D diagonal. So E is the sort of canonical matrix. So Eij is going to be, let's see, at entry Lk is delta I equals Lj equals K. So it's 1 in the ijth entry and 0 on all the other entries. So if you commute a diagonal matrix with this, you get the difference of the diagonal matrices at I and j times Eij. So what this tells you is that this gives you an eigenvector eigenvalue pair of this commutator operation, which means, I don't know if you've ever done numerical methods for finding eigenvalues. You can use a Krylov subspace technique, where if you have one diagonal matrix D, such that Di minus Dj is unique for all combinations of I and j, then if you then start commuting this matrix over and over and over again, you can use a Krylov subspace method to generate a bunch of new directions in your Lie algebra, potentially all of them, basically. Certain symmetries are imposed on the H's such that there can't exist such a diagonal matrix, but you can prove a lemma that says if you have if the differences are as distinct as possible, then you can prove this sufficient condition. So then you can prove that you can generate all trace-free matrices. So the hard step, let's say that step actually isn't that easy, but I'm just going to skip it. The real hard step is to prove that there exists a diagonal matrix which is kind of sufficiently distinct enough diagonals, which is a really weird condition, but that's what happens. And so you can find some diagonal matrices due to the special structure of the HKs. If you commute HK and H minus K, there's sort of a structure related to the complex form of the equations that if you do this commutation, you get a diagonal matrix. So the idea is I want to find a linear combination of these diagonal matrices, which satisfies this distinct differences condition. If you write everything down, fiddle around with matrix indices and play around with the fact that alpha can be chosen to be anything, you can reduce it to saying any set of four lattice guys, which satisfy some constraints are related in this way. You want to find that there's at least one K that this combination doesn't vanish. But of course, if you negate that, then you're asking to prove that there exist no solutions to the following equation. And this is, if you forget, so you have four variables in the lattice. So you have eight integer valued variables. And you have basically a Diophantine equation, because or system of Diophantine equations, because these are rational, everything is rational. If there were no Galerkin truncation, so if there's no truncation, this would be a set of rational equations that you could just multiply through by the denominators, and you would have a set of polynomial equations with integer coefficients and integer unknowns. And you want to prove whether or not you can find solutions. But you want to prove that you cannot find solutions. And then, well, there's a set of techniques for that coming from algebraic geometry. And so we use algebraic geometry methods, particularly computational algebraic geometry methods, to prove that these systems are inconsistent. There's two caveats. One caveat is that these aren't quite algebraic equations. These aren't quite polynomial systems, because the Galerkin truncation makes them not quite, they're not quite polynomials because of indicator functions snuck in because we chopped off the variables in a square. So you have to play this game where you look at all possible combinations of this indicator functions, and you get 32 options. And you have to prove that all 32 versions of this system are inconsistent. But that's okay. It's just more work for the computer. Doesn't require more work for us. Then the other thing is to realize that you have to be a little bit, well, not smart is kind of a strong term, but you can't just immediately take the system and throw it in the computer. This will work for a fixed dimension, but it will not give you a theorem that tells you all dimensions sufficiently large, which is what we want. And so you need to use, actually we use the fact that this guy is not only a set of polynomials in I, J, L, and M, but it's also a polynomial in K. So if you fiddle around with how polynomial ideals work, you can reduce it to a more complicated system of equations that are higher order. But if you prove that this more complicated system of equations is inconsistent, then you can prove it, and it applies the theorem in all dimensions sufficiently high. So this number 396 is sort of a combination of that trick to treat all dimensions and a combination of how you break up into all the different cases due to the Galerkin truncation. So this step is actually fundamentally perturbative around the infinite dimensional limit, in a sense. Anyway, so it's kind of an odd paper because it has no PDEs in it, it has no analysis in it. It's all algebra basically, which is unusual for me. Okay, so that's it. Yeah, so I hope that this work is kind of a beginning. I think there's a lot of areas for improvement, and of course the methods, as you can see, are very intrinsically finite dimensional in a lot of steps, except for this last one. And Yeah, proving the infinite dimensional case seems far off. I mean, it seems really hard to me still. At least if you want to prove it here, and it says all sufficiently high Reynolds number is chaotic, which is the regime that I care about. There might be perturbative regimes that we look at kind of bifurcation, like bifurcations right at the edge between stability and chaos, but that's another story completely. Okay, thanks for your attention, everyone.
Well, thank you very much. So if people would like to unmute and ask questions. Any questions?
So I have one. Is there any hope of getting a power of epsilon out of this? I mean, can you sort of somehow use that S star in the hyperellipticity estimate?
Mm-hmm.
And use something about how close you had to get to zero for that estimate to work?
Right.
To...
I think that might be possible. So yeah, I think that this inequality that we use is, I think it throws away a tiny bit of information, this inequality, which is, well, I have to show the proof a little bit. So this inequality is directly due to the following. I have to explain it. So when you do hyperellipticity, kind of a la Hormonal, you have your estimates. Well, when you do the L2 theory, you have sort of given you get an energy estimate for the forcing directions. Here in our proof, we're just assuming that that holds. But you don't get them actually. In fact, they're false somehow. But so we're assuming some a priori estimate on some directions. But then if you assume the a priori estimates, if you remember the formula for the generator, then what you can do is you can prove that you have this negative regularity estimate on the drift vector field. So this is related to how Hormonal did it. So you have kind of this dual space, which is sort of, in our case, is W minus 1 infinity in the forcing directions. The thing is that the argument that I'm about to use doesn't take advantage of this epsilon. In this small noise limit, this dual thing is going to 0, which it's sort of a quantification of the fact that your measure is actually converging to a solution of x0 star g equals 0. It doesn't take advantage of this epsilon. And so when you go here, so the step following the step of our theorem is to prove that this general inequality holds for sort of all smooth functions, more or less. And this is kind of how Hormonal suggested to do hyperellipticity theory. Just an excellent suggestion. But if you could sort of put an epsilon to some power here, and epsilon to some matching power here, that would do the trick for what you just said, to get a polynomial power. And I think, I mean, a polynomial power is definitely true, as you know, that it should be true. And it should be true in sort of massive generality, I think. So that's why I think that it may be possible just to get a better interpolation estimate at this step, and prove it for sort of all systems in wide classes, which I think should be true if you think about kind of just shear driven chaos, even for random perturbations of completely integrable systems should kind of have a power law epsilon. There's some details in the proof for why I don't know how to prove the interpolation inequality I just claimed, but I don't think it's impossible. I don't necessarily think it's impossible. I just think it requires a more subtle reformulation of the proof than what we did.
Thanks.
Are there other questions?
Hi, Jacob. Thanks for a great talk.
Thanks for listening.
You know, I don't know the material very well, but so you mentioned that the Lagrangian chaos and Eulerian chaos, right? So is like one, probably they're very different, but can you give us some, let's say, comparison or between these two? And the second question is this hypoelliptic forcing. So what if you don't have this hypoelliptic forcing? Is there any other regime, like a physical regime, that you want to establish this sort of the result?
Right. Well, you want to establish the result in all kinds of regimes, but let's focus on things that we have a chance of establishing the result on. So I think that it is possible. So if your forcing is not hypoelliptic, in general, your stationary measures may not be unique. Now, that's not a theorem for Navier-Stokes yet. So that is actually a theorem we're trying to prove. But we'll see how that goes. But yes, if you use non-hypoelliptic forcing, in general, you will not have unique stationary measures. And for this technique to work, you need a stationary measure that's kind of, I mean, this technique requires some regularity of the stationary measure. So you need to be able to prove stationary measure with some regularity. And yeah, so I think that the technique can work in more general cases, even with non-unique stationary measures. You can say, oh, there exists a stationary measure on which the solution is chaotic, things like that. It's a more complicated story, so I don't know exactly how it's going to happen, but I'm sure that the method will still work. And things like the MET all adapt to that case, but you have to sort of look at each individual ergodic component of all those stationary measures and stuff like that. Now, about Lagrangian chaos and Eulerian chaos, now superficially, they're actually completely different in the following sense. You can come up with examples of velocity fields which have Lagrangian chaos but not Eulerian chaos. And actually, the simplest example of this is an autonomous system which is chaotic. Right? The vector field isn't changing at all, but the trajectories are chaotic. Otherwise, you can also think of stochastic systems. So, for example, we demonstrated a velocity field like this on the torus. And these ZJs are IID Ornstein-Uhlenbeck processes. So they solve this sort of canonical, really simple SDE. This velocity field has Lagrangian chaos, so the trajectories are chaotic, but Eulerian Lyapunov exponents are negative. So if you look at two different trajectories, they converge always. So this is the picture in U. They converge exponentially fast. Does that make sense? Whereas, and similarly in Eulerian chaos, you can come up with dumb examples. We have Eulerian chaos, but not Lagrangian chaos. So a dumb example will be something like, let's take U to be, say, put some coefficient here, which is chaotic, times sine of y. So this, so like make A like the first component of the Lorentz 63 of Lorentz 63 in a chaotic regime. And now you have a velocity field which has Eulerian chaos, but it's not Lagrangian chaotic. Does that make sense? Now, of course, in real fluids at high Reynolds number, you observe and expect both. And really, if you're studying infinite dimensional fluid mechanics and you're sending the Reynolds number to infinity, in 3 dimensions, for example, you expect both Lyapunov exponents to diverge. You expect them to be like some inverse power of the Reynolds number. Oh, sorry, You expect them to be some power of the Reynolds number. So some inverse power of mu. We have no idea how to prove anything like that right now, but that's what you observe.
Okay, yeah, thank you. So look forward to the next result. Yeah.
I don't know.
Are there other questions?
I have a small question. So I have trouble seeing what exactly is specific about Navier-Stokes that you're using here. So would this work for SQG maybe with some dissipation?
Yeah. Galerkin SQG should be contained in our model. Yeah, because if you truncate the finite dimensions, then the SQG model should be able to be written in this form. And there's no regularity problems. The step that is dependent on the exact nonlinearity is the proof of the projective parabolic harmonic condition. Our method would apply to SQG actually relatively simply, because you use the structure is all the same. The only thing that's different is this C is different for SQG. So I think the only difference is this disappears. Trying to think if that's problematic or not. Because I need that it's we use that it's a polynomial in K and J and stuff like that. That's actually a good question. Actually, I think about it, I'm not sure that the technique will work for odd powers here. Because you need to be able to reduce yourself these d's here, which are some complicated function of these things. You need to be able to turn this system into a system of polynomials. So if you can't turn it into a system of polynomials, then I don't know how to prove projective harmonic conditions. So if you can kind of raise things to enough powers such that you can make everything, so that if you can make everything a polynomial, then you can use our method, not our proof. Because in some sense, we have no idea what the computer uses to prove that these equations are inconsistent. And actually, it's worth noting the systems are actually pretty large, and the computational complexity of verifying these polynomial systems is inconsistent. It's extremely high, or could be extremely high. But the computer does it really fast. But if you change how the variables are ordered, it doesn't work. So it's somehow the structure of the Navier-Stokes equations is somehow amenable to being solved in this manner. It's something like if you put in a different nonlinearity, the problem, the computations may not converge. Put into some kind of arbitrary non-structured one, but we don't know what the structure really is that the computer's using. That's the disadvantage of using a computer assisted proof, which is why we like not computer assisted proofs. Because I can't tell you, it's just the computer does something magical and it magically says that it works. So it's an interesting question. Actually, now that you mention it, I don't know off the top of my head if you can reduce it to something that can be solved with a computer. And without a computer, I don't know how to solve this.
Sure, thanks.
A small comment related to SQG. A group of us, including Nathan Glatz-Holtz, looked at a different active scalar equation called the MG equation. And that equation is even rather than odd in the way SQG is. And there it was possible to actually, roughly speaking by hand, show that the Hormonal bracket condition was satisfied. But for this MG equation, which is an active scalar equation with an even multiplier symbol.
Right, but were you able to verify this for the projective lifted process on the sphere bundle?
I'd have to look at it again to see exactly.
Yeah, because like
was Uri Faldish did the sort of by hand construction of the Hormonal brackets that worked, but definitely was making use of the evenness of the symbol.
Yeah, I mean, I think that you, I think that it was, yes. So I know the MG equation from your papers, and redoing the proof of Wynne and Jonathan Mattingly's paper for the MG equation would already be hard. So their paper, sort of Navier-Stokes, is simple enough such that verifying hypotheticity of the base process is already is relatively easy for Navier-Stokes. The MG equation is going to be much more complicated, I think.
Well,
so I think
it is a scalar equation.
Which, but so is 2D Navier-Stokes.
3D Navier-Stokes is not.
But so 3D Navier-Stokes, you can still do. Romito has the hyperellipticity, has the version of Wynne and Jonathan Mattingly's paper for 3D Navier-Stokes. But even 3D Navier-Stokes is in some sense simpler than the MG equation. In other sense, no, but in some sense it's more complicated. Now maybe the MG equation you could use this technique on. I think the 3D Navier-Stokes equation you can use this technique on as well. We just didn't do it because we didn't feel like putting 96 or 108 polynomials into the computer. But if there's a graduate student out there that's really motivated about computational algebraic geometry and just really wants this proof done, I think that Galerkin 3D Navier-Stokes is an approachable problem. Assuming that sort of the god of math is there to allow the computer to finish on time. But I think I kind of have a little bit of faith that the structure of 2D that allows it to work will somehow work in 3D. That the computer system proof will work in 3D.